In 1998, a spacecraft named Hipparcos handed astronomers a puzzle they could not quite explain. Buried in its catalogue of stellar positions and brightnesses were a handful of white dwarfs, the dense, dead embers of stars like our Sun, that appeared to be glowing with more warmth than they had any right to still possess. It was a small discrepancy, easy to dismiss as measurement error. But 2 decades later, a much sharper eye opened onto the sky, and that small discrepancy refused to go away. That eye belonged to Gaia, the European Space Agency's stellar cartography mission, and in 2019 it delivered something astronomers had never seen with this kind of clarity: a traffic jam of white dwarfs, piled up at almost exactly the same brightness and color, as if a huge fraction of them had simply stopped cooling for a while. Stars that should have been sliding steadily down the cooling curve, fading like coals pulled from a fire, were instead pausing, loitering, refusing for a time to grow any dimmer. This is where our story begins, not with a myth of eternal flames, but with a real anomaly, caught in real data, that forced physicists to ask an uncomfortable question. If the standard picture of how stars die is correct, this pileup should not exist. And when scientists find something that should not exist, they don't panic. They investigate. What they found waiting at the bottom of that investigation turned out to be one of the strangest and most quietly profound discoveries in modern stellar astrophysics, one that is still unfolding today, with the James Webb Space Telescope now probing its most extreme and most speculative edges. To understand why a pile of dead stars refusing to cool counts as a crisis, you first have to understand what a white dwarf actually is, and why astronomers thought they understood its fate so completely. Nearly every star you can see with your naked eye will, eventually, become a white dwarf. Only the most massive stars, the rare giants many times heavier than our Sun, end their lives in the violence of a supernova or collapse into a neutron star or a black hole. The vast majority of stars, including our own Sun, follow a gentler, slower path toward death. For billions of years, they fuse hydrogen into helium in their cores, holding themselves up against the crush of their own gravity through the outward pressure of nuclear fire. Eventually, the hydrogen runs low. The core contracts, the outer layers swell into a red giant, and the star begins fusing helium into carbon and oxygen. That helium to carbon step is not as straightforward as it might sound, and working out how it happens at all was itself a small scientific mystery with a memorable solution. Ordinary stellar fusion builds heavier elements by fusing 2 nuclei together at a time. But 2 helium nuclei fused together simply produce beryllium-8, an isotope so unstable that it falls back apart in less time than it takes light to cross a single atom, seemingly closing off any path toward carbon before it could begin. In the early 1950s, the British astrophysicist Fred Hoyle reasoned that carbon clearly does exist, in vast quantities throughout the universe and inside our own bodies. So nature must have found a way around this apparent roadblock. And he predicted that carbon nuclei must possess a very specific, previously unmeasured excited energy state that would allow a 3rd helium nucleus to fuse with that fleeting beryllium before it decayed, in a resonance now known as the triple alpha process. Laboratory physicists went looking for exactly the energy level Hoyle had predicted, purely from the logic that the universe's abundance of carbon demanded it, and found it precisely where he said it would be. It remains one of the most striking examples in the history of science of a prediction made not from a new experiment, but from taking an observed fact about the universe, that carbon-based life exists at all, and reasoning backward to the previously unknown nuclear physics required to make it possible. That same helium-fusing engine, running for the final active stretch of a star's life, is what produces the carbon and oxygen that will eventually make up the crystallizing core of the white dwarf this documentary has spent so long following. When even that fuel is exhausted, the outer layers drift away into space as a glowing shell called a planetary nebula, and what remains behind is the star's naked core, an object roughly the size of Earth, but carrying a mass comparable to the Sun, compressed to a density so extreme that a single teaspoon of its material would weigh several tons here on Earth's surface. The very first white dwarf ever identified sat hiding in plain sight for decades before anyone realized what it was. In 1862, the telescope maker Alvan Clark, testing a new lens, spotted a faint companion orbiting Sirius, the brightest star in the night sky. That faint companion, later named Sirius B, puzzled astronomers for half a century. Its gravity clearly showed it was almost as massive as the Sun, yet it gave off so little light that it seemed to be a tiny, dim speck. It was not until 1915, when the American astronomer Walter Adams managed to capture its spectrum, that the true strangeness became clear. Sirius B was blisteringly hot, hotter than the Sun itself, and yet almost impossibly faint, which could only mean it was absurdly small and dense, packing roughly a sun's worth of mass into a sphere not much larger than the Earth. The physicist Arthur Eddington later called it, memorably, a star whose matter had been squeezed into a state where a matchbox full of it would weigh a ton, a description that sounded at the time almost like a violation of physics itself. It took the quantum mechanics of the 1920s and Chandrasekhar's later refinements to explain how such an object could exist at all without collapsing further under its own weight. This is the white dwarf. It no longer generates energy through fusion. There is no furnace left burning inside it. What keeps it from collapsing further is not thermal pressure at all, but a strange quantum mechanical effect called electron degeneracy pressure, first worked out mathematically by the physicist Ralph Fowler in 1926 and refined shortly afterward by a young Indian astrophysicist named Subramanian Chandrasekhar. Electrons, according to the rules of quantum mechanics, cannot be squeezed indefinitely into the same space and the same energy state. As gravity tries to compress the white dwarf's core, the electrons resist, not because they are hot, but because the laws of quantum physics forbid them from being crowded any closer together. This pressure has nothing to do with temperature. It exists even if the star cools all the way down to absolute zero. Chandrasekhar arrived at his most famous result, the limit that now bears his name, during a long sea voyage from India to England in 1930, while still only 19 years old, working out on paper what would happen to a white dwarf if enough mass were piled onto it. His calculations suggested that above roughly 1.4 times the mass of the Sun, electron degeneracy pressure would simply fail to hold the star up at all, implying that sufficiently massive stellar remnants must collapse into something far stranger. When Chandrasekhar presented these results to Britain's leading astrophysicists in 1935, he was publicly and dismissively rebuked at a meeting of the Royal Astronomical Society by Arthur Eddington, then the most prominent astrophysicist in the world, who declared that nature must find some way to prevent such an absurd outcome, and effectively ridiculed the young scientist's mathematics in front of his peers. Chandrasekhar was, in fact, correct, and Eddington was wrong, though it would take decades, and the eventual confirmation of neutron stars and black holes as real astrophysical objects, for the physics community to fully vindicate him. Chandrasekhar received the Nobel Prize in Physics in 1983, more than 50 years after that fateful sea voyage, a reminder that even the most eminent scientific authorities can be spectacularly wrong, and that the history of astrophysics is full of ideas that were mocked before they were proven essential. That last detail matters enormously, because it means a white dwarf is, in essence, a stable, inert ember. It has no ongoing power source. Whatever heat remains, locked inside it from its earlier life as a fusion-powered star, is all it has left. And from the moment it forms, that heat can only leak away, radiating slowly into the emptiness of space. Astrophysicists in the mid-20th century built detailed models of exactly how this cooling should proceed, because white dwarfs are so dense and so hot when they form, often north of 100,000 degrees at the surface. They start out cooling quickly, but as billions of years pass, they settle into a long, gentle decline, growing steadily fainter and redder, like a dying campfire settling into ash. Given a star's mass and its composition, you could, in principle, calculate its age, just from how much light it still gives off. White dwarfs became, in this sense, some of the most reliable clocks in the galaxy. Astronomers have used the coolest, faintest white dwarfs in globular clusters to independently check the age of the universe itself, and their answers lined up beautifully with estimates from cosmic microwave background data and from the ages of the oldest surviving stars. The physicist Leon Mestel worked out the mathematical backbone of this cooling process in 1952 describing how a white dwarf, once its outer layers stop generating any energy, essentially behaves like a hot solid object, slowly radiating its stored heat away through a thin, insulating outer atmosphere, a picture that came to be known as Mestel cooling. In the earliest stage of a white dwarf's life, immediately after it forms, the dominant process actually is not the leisurely radiation of light at all, but a far stranger and faster drain, neutrino cooling. At the blistering temperatures of a newly formed white dwarf, exotic particle processes inside the hot plasma produce vast numbers of neutrinos, ghostly particles that interact so weakly with ordinary matter that they stream straight out of the star almost instantaneously, carrying enormous amounts of energy away with them in a comparative flash. Cosmically speaking, that lasts only the first few 100 million years. Only once the star has cooled enough for this neutrino channel to shut off does the slower, more familiar process of photon cooling, ordinary light radiating from the surface, take over as the dominant mechanism, and it is this second, much longer phase, stretching across the following billions of years, that the crystallization and neon sedimentation processes described earlier step in to modify. Understanding both phases in detail and knowing precisely where one hands off to the other for a star of any given mass is what allows astronomers to translate a measured brightness and color into a precise age in the first place. The entire foundation the Gaia pileup rested on when it first revealed itself as an anomaly rather than a mistake. There's an added wrinkle worth knowing, because it will matter later in this story. The Chandrasekhar limit is not just an abstract number describing how large a white dwarf can grow before electron degeneracy pressure can no longer hold it up. It is also, indirectly, one of the reasons the universe has a reliable cosmic yardstick at all. When a white dwarf in a binary system slowly siphons material from a companion star, or when two white dwarfs spiral together and merge, pushing the combined mass past roughly 1.4 times the mass of the Sun, the delicate balance that Chandrasekhar described breaks down catastrophically, and the star detonates as a type Ia supernova, an explosion so consistent in its peak brightness that astronomers use it as a standard candle to measure distances across billions of light years, work that eventually led to the surprise discovery in the late 1990s that the expansion of the universe itself is accelerating. It is a strange thread to pull on, the same delicate quantum pressure that lets an ordinary white dwarf sit quietly, cooling for billions of years, is also the trigger mechanism behind one of the most important measuring tools in all of modern cosmology. That accelerating expansion discovery, credited to two independent research teams led by Saul Perlmutter and by Brian Schmidt and Adam Rees, and honored with the Nobel Prize in Physics in 2011, revealed that roughly 70% of the universe's total energy budget consists of something even stranger than dark matter, an even more mysterious component called dark energy, a persistent pressure pushing space itself apart at an ever-increasing rate. It's worth being precise here, because the two are often confused in casual conversation. Dark matter, clumps and clusters, providing extra gravity that holds galaxies and clusters together, while dark energy does the opposite, acting as a smooth, uniform pressure spread evenly throughout space, driving galaxies apart from one another on the very largest scales. Both remain among the biggest open questions in physics, and remarkably, both were first pinned down using stars, one using the reliable clockwork of ordinary white dwarf detonations, the other using the reliable clockwork of white dwarf cooling itself. Building the tools to actually measure a white dwarf's temperature and brightness precisely enough to test any of this took a long time. Astronomers plot stars on what's called a color magnitude diagram, comparing how bright an object appears against how blue or red its light is. Hot young white dwarfs sit toward the blue, bright end of this diagram. Old, cool ones drift toward the faint, red end, tracing out a smooth, predictable curve as an entire population ages together. For most of the 20th century, this technique was limited by how faint an object a given telescope could reliably measure, which meant only the brighter, younger white dwarfs nearby could be studied in detail. It was only with space-based platforms, first Hipparcos, then Gaia, and now Webb, that astronomers gained the sensitivity and precision needed to trace this cooling curve all the way down to its faintest, oldest end, and it was precisely at that faint end In 2019, that the pileup appeared. Building the tools to actually measure a white dwarf's temperature and brightness precisely enough to test any of this took a long time. Astronomers plot stars on what's called a color magnitude diagram, comparing how bright an object appears against how blue or red its light is. Hot young white dwarfs sit toward the blue, bright end of this diagram. Old, cool ones drift toward the faint, red end, tracing out a smooth, predictable curve as an entire population ages together. For most of the 20th century, this technique was limited by how faint an object a given telescope could reliably measure, which meant only the brighter, younger white dwarfs nearby could be studied in detail. It was only with space-based platforms, first Hipparcos, then Gaia, and now Webb, that astronomers gained the sensitivity and precision needed to trace this cooling curve all the way down to its faintest, oldest end, and it was precisely at that faint end, in 2019, that the pileup appeared. The scale of the Gaia mission is worth pausing on, because it explains why this pileup, once it appeared, could be trusted rather than dismissed as a fluke. Since its launch in December of 2013, Gaia has been repeatedly scanning the entire sky from its perch nearly 1 million miles from Earth, measuring the positions, distances, motions, and brightnesses of nearly 2 billion stars, an undertaking so vast that no single team of astronomers analyzes it by hand. Instead, the raw measurements pour into enormous public catalogs, released in stages, that research groups all over the world mine for patterns. The white dwarf pileup did not emerge from a single targeted observation of a single suspicious star. It emerged from statistics, from tens of thousands of individual white dwarfs, each one an unremarkable data point on its own, that only revealed their shared secret once plotted together on the same diagram. That is part of what makes modern astrophysics feel different from the astronomy of a century ago. Increasingly, the biggest discoveries are not made by staring harder at one object, but by building datasets large enough that a pattern too subtle for any single observation becomes unmistakable once millions of data points are laid side by side. That is precisely why the Gaia pileup was so startling. If the cooling clock were running smoothly, there was no reason for such a large population of white dwarfs to be clustered at nearly identical brightness and temperature. Something, somewhere in their interiors, was interrupting the clock. Something was putting the brakes on the cooling process itself. Before we follow the scientists down the path they took to solve this, it's worth pausing on why this kind of question matters beyond a narrow corner of astrophysics. If you find questions like this fascinating, the kind of puzzle where the universe quietly breaks its own rulebook and forces us to write a new one, it's worth spending a moment thinking about how many of these anomalies are hiding in plain sight in data we already have, waiting for someone patient enough to notice the pattern. That patience, more than any single flash of genius, is usually what turns a strange blip in a chart into a genuine discovery. The first serious clue came from a mechanism that, on paper, had been predicted decades earlier, but never confirmed observationally: crystallization. A white dwarf's interior is not a simple uniform blob of gas. It is primarily a mixture of carbon and oxygen, the ashes of the helium fusion that powered the star's red giant phase, wrapped in a thin outer envelope of hydrogen and helium. As this core cools over billions of years, the carbon and oxygen ions inside it slow down. Eventually, they can slow down enough that instead of behaving like a fluid, jostling freely past one another, they lock into an orderly, repeating lattice, the same basic transition that turns liquid water into ice. Except here, the temperatures involved are still measured in millions of degrees, and the pressure is roughly 1 million times that at Earth's core. When a liquid freezes into a solid, it releases energy. This is true of water freezing into ice, and it is true on a far grander scale of a white dwarf's core freezing into a crystal. That released energy, called latent heat, works its way outward and adds extra warmth to the star, slowing its rate of cooling exactly at the moment theorists needed to explain the Gaia pileup. There's a strange, almost poetic detail buried in this physics, because a white dwarf's interior is overwhelmingly carbon, and because that carbon is being squeezed by pressures roughly 1 million times greater than anything at the center of the Earth. Some astrophysicists have half-jokingly noted that, over long enough timescales, a fully crystallized white dwarf is, structurally speaking, an enormous crystal of carbon, not unlike a diamond, albeit one the size of a planet, sitting quietly in the dark, its glow slowly fading as billions of years pass. In a Nature paper published in 2019, the astrophysicist Pierre-Emmanuel Tremblay and his colleagues showed that crystallization fit the observed pileup remarkably well. For the first time, astronomers had direct observational evidence that the interiors of white dwarfs really do freeze solid, an idea that had existed in theoretical papers since the 1960s, but had never before been confirmed by watching it happen. Statistically, across an enormous population of stars. It's a beautiful piece of science, and it would be a satisfying place to end the story. Except for one thing. Crystallization alone could not account for everything astronomers were seeing. Some white dwarfs, particularly a subset of unusually massive ones, were cooling even more slowly than the crystallization models predicted. There was still heat coming from somewhere, and the standard picture of a simple carbon-oxygen freeze was not quite enough to explain all of it. The next piece of the puzzle involved an element most people have never heard of outside a chemistry classroom: neon. Specifically, a heavier isotope called neon-22. As a white dwarf's core solidifies, it does not freeze all at once uniformly, like a glass of water left in a freezer. Different elements within the mixture have slightly different properties, and as crystallization proceeds, denser trace elements like neon-22 get squeezed out of the newly forming solid crystal and sink, slowly toward the center of the star, while lighter material rises to take its place. This process, sometimes called gravitational settling or phase separation, converts gravitational energy into heat, in much the same way that a stone sinking through water releases energy as it falls. Theoretical work by researchers including Simon Blouin and Jérôme Daligot modeled this neon sedimentation process in detail, and in 2019 and the years that followed, observational teams found white dwarfs, especially in old, dense star clusters, that were cooling anomalously slowly in ways that matched these predictions closely. Some ultramassive white dwarfs appeared to be taking billions of years longer to cool than a simple model would suggest, their interiors acting less like a single ember and more like a layered furnace, still generating trickles of heat from the slow, gravitational rearrangement of their own internal chemistry. So by the early 2020s, the mystery of the stalled white dwarfs had a solid, evidence-backed answer, built from two real physical processes: the release of latent heat as carbon and oxygen freeze into a crystal lattice, and the release of gravitational energy as heavier trace elements like neon-22 sink through that crystallizing interior. Neither of these mechanisms is exotic in the sense of breaking known physics. Both are consequences of ordinary thermodynamics and gravity, operating under the extreme pressures found deep inside a stellar remnant. What makes them remarkable is not that they violate the rules, but that they reveal just how much complexity and structure can hide inside an object that, for most of the 20th century, astronomers had treated as a simple, inert clinker with nothing left to do but fade quietly away. This matters enormously for how we should think about the rest of this story, because it draws a firm line between two very different categories of claim. On one side sits confirmed observation. White dwarfs really do cool more slowly than the simplest models predict, and we have identified real, physically grounded mechanisms, crystallization and elemental sedimentation, that account for a great deal of that discrepancy. This is settled, published, peer-reviewed science, backed by Gaia's enormous stellar census and multiple independent theoretical models. On the other side sits something far more speculative, a hypothesis that some researchers have proposed as an additional, exotic contributor to stellar heating in specific extreme environments: the idea that dark matter itself might, under the right conditions, add its own quiet warmth to the interiors of dense stellar remnants. To understand where that idea comes from, and why serious physicists take it seriously enough to test it, we need to talk about dark matter itself, and about a much stranger and more speculative cousin of the white dwarf story: the idea of stars powered not by fusion, but by the annihilation of invisible particles. The story of dark matter's discovery is, in its own way, just as strange as anything in this documentary. And it began with an irritable, brilliant Swiss astronomer named Fritz Zwicky. In 1933, studying the Coma Galaxy cluster, a vast swarm of thousands of galaxies bound together by gravity. Zwicky measured how fast individual galaxies within the cluster were moving and found something that made no sense. The galaxies were moving so quickly that, based on the visible mass of the cluster alone, the whole structure should have flown apart long ago, the way a poorly tied bundle of balloons scatters the moment the string is cut. Zwicky concluded that some unseen mass, far more than could be accounted for by the visible stars and gas, must be holding the cluster together, and he gave it a name that has stuck in translation ever since: dunkle materia, dark matter. For decades, most astronomers treated this as an interesting curiosity rather than a central mystery of the universe. That changed in the 1970s, when the American astronomer Vera Rubin, working with the instrument maker Kent Ford, began carefully measuring how fast stars orbit at different distances from the centers of spiral galaxies. If a galaxy's mass were concentrated mostly in its visible core, the way its light suggested, stars near the outer edge should orbit noticeably slower than stars near the center, the same way that outer planets in our solar system take longer to circle the sun than inner ones. Instead, Rubin and Ford found that stars far out in the disk were moving just as fast as stars near the center, tracing out what astronomers now call a flat rotation curve. The only way to explain this was if each galaxy were embedded in a much larger, invisible halo of mass, extending far beyond the visible starlight, exerting gravity, but emitting no detectable light of its own. Rubin's meticulous, repeated measurements across dozens of galaxies turned dark matter from a curious footnote into one of the central open problems in physics, a status it retains to this day. Roughly 85% of all the matter in the universe is something we cannot see directly. We know it is there because of its gravity. It holds spinning galaxies together when their visible stars alone are not nearly massive enough to do the job. It bends and magnifies light from background galaxies as it passes through massive clusters, an effect called gravitational lensing, and it left its fingerprints on the cosmic microwave background, the faint afterglow of the Big Bang, in patterns that modern telescopes have mapped with extraordinary precision. That afterglow deserves a moment of its own, because it is arguably the single strongest piece of evidence that dark matter is real, and not simply a sign that our theory of gravity needs revising. When the European Space Agency's Planck satellite mapped the cosmic microwave background across the entire sky between 2009 and 2013, it revealed a pattern of tiny temperature fluctuations, differences of only a few millionths of a degree from one patch of sky to another, left over from sound waves rippling through the hot plasma of the infant universe less than 400,000 years after the Big Bang. The precise pattern of peaks and valleys in those fluctuations depends sensitively on how much ordinary matter and how much additional, gravitating but non-interacting matter was present at that early moment, and the fit that best matches Planck's data requires roughly 5 times more dark matter than ordinary matter, an independent confirmation, arrived at through an entirely different method than Zwicky's cluster measurements or Rubin's rotation curves, pointing to the same conclusion. It's worth noting that dark matter is not the only deep mystery tangled up in that same early moment of cosmic history. Ordinary matter itself, the atoms making up stars, planets, and every living thing, presents its own unsolved puzzle. According to the equations of particle physics, the hot, energetic early universe should have produced matter and its mirror image counterpart, antimatter, in almost exactly equal amounts, and the two should have annihilated each other completely, leaving behind a universe of pure light with no matter at all. Something must have tipped the balance ever so slightly in favor of matter, a process physicists call baryogenesis, and the details of exactly how and why that tiny imbalance occurred remain unresolved. A puzzle sitting right alongside the dark matter question at the frontier of fundamental physics. Some of the same theoretical frameworks that predict WIMP-like dark matter particles also offer possible explanations for this matter-antimatter imbalance, which is part of why so much of modern particle physics research treats these two mysteries as connected threads of the same larger unsolved story, rather than as unrelated curiosities. In January of 2026, using new James Webb Space Telescope data covering nearly 800,000 galaxies, Astronomers, including Bahram Mobasher at the University of California, Riverside, published one of the most detailed maps ever made of how dark matter is distributed across a patch of sky, tracing the way it forms a vast filamentary cosmic web that ordinary matter, including every star and galaxy we can see, tends to follow. This is not speculation. Dark matter's gravitational influence on the universe is about as well established as any result in modern cosmology. What remains genuinely unknown, despite decades of searching, is what dark matter actually is, at the level of individual particles. The leading family of candidate explanations, broadly known as weakly interacting massive particles, proposes that dark matter consists of particles that interact with ordinary matter almost entirely through gravity, and perhaps, very rarely, through an extremely feeble version of the weak nuclear force, the same force responsible for certain types of radioactive decay. If that picture is correct, then every second, unimaginable numbers of these particles are passing directly through the Earth, through your body, through the pages of any book, almost entirely without interacting. Almost. It is in that word, almost, that this entire second thread of the story lives. It's worth being fair to the full landscape of ideas here, because weakly interacting massive particles are the leading candidate for dark matter. But they are far from the only one physicists take seriously, and an honest account of this search has to acknowledge the competition. Some physicists favor axions, hypothetical particles far lighter than WIMPs, originally proposed in the late 1970s to solve an unrelated puzzle in nuclear physics, which would behave more like a faint pervasive wave than a swarm of billiard balls, and which experiments, like the axion dark matter experiment, are searching for, using powerful magnetic fields designed to coax a stray axion into converting into a detectable photon. Others favor sterile neutrinos, a hypothetical heavier cousin of the ordinary neutrinos already known to exist, which would interact with normal matter even more feebly than WIMPs and would leave a different, distinctive fingerprint in the distribution of the smallest galaxies. Still others have explored the possibility that dark matter is not a new particle at all, but ordinary matter locked away in a form we simply can't see easily, such as black holes formed in the first fraction of a second after the Big Bang, so-called primordial black holes, an idea that astronomers have tested by watching for the brief, telltale brightening that occurs when such an object drifts in front of a background star and briefly magnifies its light through gravitational lensing, a technique used by long-running survey projects like OGLE and EROS. Each of these candidates makes its own specific, testable predictions, and each has been narrowed, though not eliminated, by results so far. It is specifically the WIMP hypothesis, with its built-in tendency to scatter off ordinary nuclei, that predicts the kind of stellar capture and heating this documentary is focused on. If dark matter instead turns out to be axions or primordial black holes, the white dwarf and neutron star heating signal described here would look very different, or might not exist in a detectable form at all. That uncertainty is itself part of why astronomers pursue several very different search strategies simultaneously, rather than betting everything on one. Physicists have long speculated that certain unusually dense astronomical objects, because of their extreme gravity, might act as natural traps for dark matter particles. Imagine a WIMP moving through the galaxy at a significant fraction of the speed of light, passing near a white dwarf or a neutron star. Occasionally, instead of sailing straight through, it scatters off an atomic nucleus or an electron inside the star, the same way a billiard ball loses some of its speed in a glancing collision. That single collision robs the dark matter particle of just enough kinetic energy that it can no longer escape the star's gravity. It is captured. Over time, more and more particles scatter, lose energy, and sink toward the object's center, accumulating in a dense, invisible cloud right at the star's heart. What happens next depends on the exact properties of the dark matter particle, something physicists still don't know. In one scenario, called annihilation, two dark matter particles meeting at the star's core destroy each other, converting their mass directly into energy according to Einstein's famous relationship between mass and energy, and that energy heats the surrounding stellar material. In another scenario, sometimes called kinetic heating, the particles never annihilate at all. They simply keep colliding with the star's normal matter over and over, gradually depositing their kinetic energy as heat, The same basic principle as friction, just happening deep inside a stellar remnant instead of between two solid surfaces. A landmark 2017 paper by the physicists Masha Bayakhtar, Joseph Bramante, Shirley Waishi Lee, Tim Linden, and Nirmal Raj worked through the details of this kinetic heating mechanism for neutron stars, and their calculations suggested something remarkable. In regions of the galaxy where dark matter is unusually dense, particularly near the galactic center, this heating could, in principle, raise a neutron star's surface temperature to a level detectable in infrared light, using instruments with the sensitivity of the James Webb Space Telescope. It's worth pausing here to appreciate just how extreme a neutron star actually is, because that extremity is exactly what makes it such an efficient dark matter trap in these calculations. When a star considerably more massive than our Sun exhausts its nuclear fuel, it does not settle gently into a white dwarf. Its core collapses so violently that protons and electrons are crushed together into neutrons, and the collapse only halts when a different kind of quantum degeneracy pressure, this time among the neutrons themselves, finally pushes back hard enough to stop the crush. What remains is an object roughly the size of a city, 10 or so miles across, yet containing more mass than our entire Sun, so dense that a single sugar cube-sized piece of it would weigh about as much as a mountain here on Earth. These objects were purely theoretical until 1967, when a graduate student named Jocelyn Bell Burnell, working with a radio telescope at Cambridge, noticed a strange, impossibly regular pulse of radio signals repeating every 1 1/3 seconds. For a brief, half-serious moment, the research team nicknamed the source Little Green Men, wondering if they had detected a deliberate signal, before realizing they had instead found something almost as astonishing: a rapidly spinning neutron star, its beam of radiation sweeping past Earth with every rotation like a cosmic lighthouse, a class of object now known as a pulsar. Because neutron stars pack so much mass into such a small radius, their surface gravity, and therefore their escape velocity, is vastly higher than that of a white dwarf, which means any passing dark matter particle that scatters within one is far more likely to be captured rather than simply deflected. This is precisely why theorists like Bayakhtar and her collaborators focused their earliest calculations on neutron stars rather than white dwarfs. For a given density of surrounding dark matter, a neutron star should, in principle, be an even more effective trap, making it one of the most promising places in the galaxy to look for this kind of heating signal, assuming one exists at all. Some neutron stars take this extremity even further, into a subclass called magnetars, objects wrapped in magnetic fields so intense, sometimes a quadrillion times stronger than Earth's own magnetic field, that if one were to pass within a couple 100,000 miles of Earth, its field alone could scramble the magnetic strip on every credit card on the planet and disrupt the electrical activity in the human nervous system. These are not the objects at the center of the dark matter heating search discussed in this documentary, but they illustrate a broader theme worth holding on to. Even within a single category of stellar remnant, nature produces an enormous range of extremity, from placid, isolated pulsars ticking along steadily for millions of years, to violent, unpredictable magnetars capable of unleashing sudden bursts of gamma rays detectable from other galaxies. Any search for a subtle signal like dark matter heating has to be conducted against this rich, varied backdrop of ordinary neutron star behavior, distinguishing a faint, steady infrared excess from the far more dramatic and already well-documented ways these objects can surprise us. It's worth comparing this approach to the more familiar dark matter hunts happening here on Earth, because the contrast helps explain why astronomers find the stellar heating idea so appealing. Deep underground, in facilities like the Xenon experiment beneath a mountain in central Italy, or the LX Zeppelin detector buried nearly a mile down an old gold mine in South Dakota, physicists have built vats of ultra-pure liquid xenon, watched over by extraordinarily sensitive light sensors, all in the hope of catching the faint flash produced if a single dark matter particle happens to strike a xenon nucleus. These experiments have grown more sensitive year after year, and each new result rules out more of the possible territory where a WIMP-like dark matter particle could be hiding, without yet producing a confirmed detection. It's worth noting that this field has not been entirely free of claimed detections either. And one long-running episode illustrates why the physics community demands independent replication before accepting any result, no matter how statistically striking it first appears. Since the late 1990s, an experiment called DEMA and its successor, Dama/Libra, buried beneath a mountain in Italy, has reported a small but persistent yearly variation in the rate of detected particle interactions in its sodium iodide crystals, rising and falling with the seasons in a pattern the team argues matches exactly what would be expected if the Earth were periodically moving faster and slower through a surrounding sea of dark matter as it orbits the Sun. The claim has now persisted in the same collaboration's data for more than 2 decades, and yet no other experiment using different detector materials but searching for the same fundamental signal has managed to independently confirm it, despite several being sensitive enough that, if the simplest interpretation of Dama's result were correct, they should have seen a corresponding signal too. The disagreement remains unresolved, a reminder that in a field this difficult, an intriguing pattern in one dataset, however statistically significant it appears on its own, only becomes an accepted discovery once other independent teams, using different equipment and methods, see the same thing. A white dwarf or neutron star, by contrast, offers something no laboratory vat of xenon ever could, a detector with the mass of an entire star, sitting in place for billions of years, continuously accumulating any dark matter that happens to scatter within it. The trade-off is that instead of a clean laboratory signal, astronomers have to tease a subtle temperature anomaly out of an object that already has its own complicated internal physics, the crystallization and sedimentation heating discussed earlier, to account for first. Physicists sometimes describe the search for WIMPs as unfolding along 3 complementary fronts, and it helps to know all 3, because the stellar heating idea sits at an interesting intersection of 2 of them. It's worth pausing on the fact that white dwarfs are not all identical either, because that variety turns out to matter for how confidently astronomers can trust any given star's measured cooling age. Spectroscopists classify white dwarfs by what their thin outer atmosphere is made of, since heavier elements settle out of that atmosphere astonishingly quickly under the star's intense surface gravity, leaving only whatever element happens to be floating on top. The most common type, designated DA, shows an atmosphere dominated by hydrogen. A second common type, DB, shows helium instead. Rarer types, including DQ, whose atmosphere is streaked with carbon dredged up from deeper in the star, and DZ, contaminated with heavier metals, likely from the shredded remains of small rocky planets or asteroids that wandered too close and were torn apart by the star's gravity, reveal a violent, complicated history playing out even after a star's fusion has ended, untangling exactly which cooling model applies to which spectral type, and how confidently a given star's composition can be pinned down from its light alone, is a painstaking, ongoing task. And it is precisely the kind of detailed, unglamorous bookkeeping that has to be done correctly before anyone can respond to a claim of anomalous heating with real scientific confidence, rather than simply reacting to an exciting headline. Direct detection experiments, like the underground xenon detectors, wait patiently for a dark matter particle to strike ordinary matter here on Earth. Indirect detection experiments instead look for the byproducts of dark matter interacting or annihilating somewhere out in the cosmos, whether that byproduct is a flash of gamma rays from the galactic center or, in this case, a faint excess of infrared heat radiating from an old stellar remnant. And collider experiments, like the enormous Large Hadron Collider straddling the border of France and Switzerland, attempt to manufacture dark matter particles directly by smashing ordinary particles together at nearly the speed of light and searching for missing energy that would indicate an invisible particle had been created and escaped detection. Decades into this 3-pronged search, physicists sometimes refer to the once favored WIMP miracle, the striking coincidence that a particle with roughly the mass and interaction strength needed to explain dark matter's abundance would also naturally arise from certain well-motivated extensions of particle physics, a coincidence that made WIMPs the leading candidate for so long. As collider searches at the Large Hadron Collider and underground direct detection experiments have steadily ruled out large portions of the simplest WIMP possibilities without finding a confirmed signal, that miracle has looked less certain than it once did. which is part of why physicists have broadened their search to include axions, sterile neutrinos, and astrophysical probes like the white dwarf and neutron star heating story at the center of this documentary. The idea of using a star as a natural dark matter trap did not begin with white dwarfs and neutron stars, and it's worth mentioning its closer, more familiar cousin, because it has already been tested for years using an entirely different kind of detector. Our own sun, sitting at the center of the solar system, should, according to the same basic capture physics described earlier, also be gathering dark matter particles as they scatter within it, sinking toward its core over billions of years. If those particles occasionally annihilate once trapped, the collision should produce, among other byproducts, high-energy neutrinos capable of escaping the sun's dense interior, essentially unimpeded, since neutrinos interact so weakly with ordinary matter that even a star's crushing density barely slows them down. The IceCube Neutrino Observatory, an enormous detector built from more than 5,000 light sensors frozen deep into the ice of Antarctica, has spent years searching for exactly this signature, an excess of high-energy neutrinos streaming from the direction of the sun, beyond what ordinary solar physics would produce. So far, IceCube and similar experiments have found no confirmed excess, a null result that has already ruled out large regions of the possible dark matter parameter space for certain interaction types. This solar search shares the same underlying logic as the white dwarf and neutron star story: gravitational capture followed by a search for a resulting byproduct. But it targets a star we already understand intimately, orbited daily by our own planet rather than a distant, ancient stellar remnant near the crowded galactic center, illustrating just how many different corners of the sky physicists have learned to turn into makeshift dark matter laboratories. This is the moment where the outline that inspired this documentary starts pointing towards something real. But it is important to be precise about exactly what is real and what is not. No one has yet observed a confirmed case of dark matter heating a white dwarf or a neutron star. What exists as of early 2026 is a mature, carefully worked out theoretical prediction published in respected physics journals, describing what such heating would look like if it existed, and identifying the telescopes, Webb among them, that would be sensitive enough to catch it if it does. The searches are ongoing. The signal, if it is there at all, has not yet been confirmed. A closely related and even more speculative idea has actually generated more public attention, and it is worth separating clearly from the white dwarf story, because the two are often blurred together in popular coverage. To appreciate why anyone would propose something as strange as a star powered by dark matter instead of fusion, it helps to picture the environment those first stars would have formed in. In the few 100 million years after the Big Bang, a period astronomers call cosmic dawn, the universe contained no elements heavier than lithium. Every carbon, oxygen, and iron atom in your body, in this planet, in every star you can see tonight, had yet to be forged, because that forging only happens inside stars and in the explosions that end their lives. The very first stars, often called population 3 stars, would have condensed out of pristine clouds of pure hydrogen and helium, gas left over directly from the Big Bang, gathering in the densest knots of the invisible dark matter scaffolding that Vera Rubin's work, and decades of research since, has shown pervades the early universe. Standard theory predicts these first stars should have been unusually massive and short-lived, burning through their fuel in a few million years before exploding as supernovae and seeding the cosmos with the heavier elements that would eventually make planets and life possible. The dark star hypothesis proposes a strange detour on the way to that standard picture, that in the very densest pockets of primordial dark matter, before an object had fully ignited nuclear fusion at all, the trickle of energy from dark matter annihilation could have been enough, on its own, to hold a huge puffy cloud of hydrogen and helium up against collapse, delaying or entirely preventing ordinary fusion from ever beginning, and allowing the object to grow to an enormous size by continuing to draw in surrounding gas. In 2007, the theoretical physicist Catherine Fries and her collaborators proposed the concept of dark stars. Enormous, puffy objects made almost entirely of primordial hydrogen and helium, forming in the very early universe, but held up against gravitational collapse not by nuclear fusion, but by the annihilation of dark matter particles trapped inside them. These would not be white dwarfs or neutron stars at all, but a hypothetical first generation of stars, existing only in the first few 100 million years after the Big Bang, before enough dark matter had been consumed or diluted for the effect to fade and ordinary fusion-powered stars to take over. Finding candidates for objects this distant depends on an observing technique that is itself worth understanding, because it explains where these controversial dark star candidates actually came from. Programs like the JWST Advanced Deep Extragalactic Survey, known by the acronym JADES, point Webb at a single small patch of sky and stare at it for an enormous cumulative exposure time, sometimes many hundreds of hours, allowing the telescope to gather enough faint, ancient light to detect galaxies and other objects from when the universe was only a few % of its current age. Because the universe has been expanding for the entire time that light has been traveling toward us, the light from these earliest objects gets stretched to longer, redder wavelengths, an effect called redshift, which is precisely why an infrared telescope like Webb, rather than an ordinary optical telescope, is required to see them at all. Their light has been stretched clean out of the visible spectrum by the time it reaches us. Among the many thousands of faint smudges these deep field surveys have revealed, a handful stood out as unusually compact and unusually bright for their inferred distance. Exactly the kind of anomaly that prompted Fries and her colleagues to propose the dark star interpretation in the first place. In 2023, Fries, along with Cosmin Auli and Gillian Paulin, published a paper in the Proceedings of the National Academy of Sciences, arguing that several of these unusually bright, unusually red objects, corresponding to a time when the universe was only a few 100 million years old, were better explained as candidate dark stars than as ordinary early galaxies. It's a genuinely exciting proposal, and it remains an active, contested area of research, with other astronomers offering alternative explanations for the same objects, including compact, rapidly forming galaxies and actively feeding supermassive black holes. As of the most recent published work, the dark star interpretation has passionate proponents and equally serious skeptics, and the debate has not been settled. So here is where the honest version of this story stands. We have one confirmed, observationally verified phenomenon. Ancient white dwarfs really do sometimes cool more slowly than expected, and the explanation lies in real, non-exotic physics. The release of latent heat during crystallization and the release of gravitational energy during the sinking of heavier elements like neon-22 through the freezing core. We have one serious, actively pursued but unconfirmed hypothesis that dark matter capture and either annihilation or kinetic scattering could, in principle, provide an additional exotic heating mechanism for extremely dense stellar remnants, particularly in dark matter-rich environments like the galactic center or dwarf spheroidal galaxies, and that James Webb's infrared sensitivity makes it one of the best instruments ever built for testing that idea. And we have a separate, related but distinct hypothesis about a hypothetical population of dark matter-powered dark stars existing only in the universe's earliest few 100 million years, for which a handful of James Webb candidates have been proposed but not confirmed. None of these ideas require breaking the laws of thermodynamics. None of them describe stars that are literally immortal or that will burn forever. What they describe at most is a delay, a slower decline, a longer twilight, powered either by internal chemistry we now understand quite well, or, potentially, by an exotic and still unconfirmed trickle of energy from the dark sector of the universe. It's a story about stars cheating the clock a little, not about stars cheating death altogether. If you find yourself wanting to actually see how astronomers tell these two kinds of heating apart in real data, or how a cooling curve for a star even gets measured in the first place, it's worth spending a few minutes digging into how Gaia and Webb build these enormous stellar catalogs. Understanding the tools makes the eventual answer, whatever it turns out to be, far more satisfying than just hearing the headline. The white dwarf pileup was not the last surprise these dead stars had in store. And it's worth mentioning a second, more recent anomaly, because it shows just how much ordinary, non-exotic strangeness is still being uncovered in this population, even without invoking dark matter at all. The Zwicky Transient Facility, a wide-field survey camera mounted on a telescope at Palomar Observatory in California, has spent recent years repeatedly scanning the sky for objects that change brightness, and in the process it has turned up white dwarfs behaving in ways standard cooling models never anticipated. Some spinning on their axis in under a minute, some locked in binary pairs so tight that they orbit each other in a matter of hours, and some showing wildly variable brightness caused by enormous magnetic fields, millions of times stronger than anything found on Earth, twisting the star's atmosphere and channeling material into hotspots on its surface. None of these discoveries point to dark matter. They point instead to a rich, varied population of stellar corpses shaped by their entire prior history, whether they merged with a companion, stripped material from a neighbor, or simply span up during their violent formation, all of which reinforces the same broader lesson this documentary keeps returning to. White dwarfs are far more individually varied and dynamically interesting objects than the simple picture of an inert, cooling ember ever suggested, and any search for something as subtle as a dark matter-heating signal has to be able to separate that signal from an increasingly long list of ordinary, already understood sources of surprising behavior. It's worth dwelling for a moment on just how difficult this kind of detection actually is, because it explains why the question remains open even with some of the most powerful telescopes ever built pointed directly at it. A white dwarf that has been cooling normally for 10 billion years might have a surface temperature of only a few thousand degrees, faint and cool by stellar standards. If dark matter heating were adding even a modest amount of extra energy, the resulting temperature boost could be small in absolute terms, difficult to distinguish from ordinary scatter in a population of otherwise similar stars, and easy to confuse with the crystallization and sedimentation effects that we already know are at work. Untangling a subtle dark matter signal from these established, non-exotic heating mechanisms requires enormous, carefully selected samples of white dwarfs with well-measured ages, masses, and compositions. Exactly the kind of dataset that Gaia has been building for stars within a few thousand light-years of Earth, and that Webb, with its ability to resolve individual faint, cool stars even in crowded ancient star clusters, is now extending to much older and more distant stellar populations. Globular clusters have become one of the most promising hunting grounds for this kind of search. These are ancient, tightly packed swarms of hundreds of thousands of stars, often more than 10 billion years old, orbiting within and around our galaxy, because every star in a given cluster formed at roughly the same time from the same initial cloud of gas. Their white dwarfs provide something astronomers rarely get: a large population of stellar remnants with a shared, well-constrained age. In 2025, a team led by Maurizio Solaris used James Webb infrared observations of the white dwarf population in the cluster 47 Tucanae, one of the brightest and most studied globular clusters in the sky, to measure its age with impressive precision, arriving at a value of 11.8 billion years, consistent with independent age estimates from the cluster's brighter, more massive stars. Studies like this are not themselves hunts for dark matter heating, but they are laying the essential groundwork, building the precise, reliable cooling age relationships against which any future anomalous excess of heat, should one ever be confirmed, would have to be measured. Webb's ability to pick out extraordinarily faint objects sitting right next to bright ones has already produced a preview of exactly the kind of precision this search will eventually depend on, in a different but closely related corner of white dwarf science. The white dwarf, known as WD0806-66, has a companion, an extremely cold, faint object called a Y dwarf, sitting at such a wide separation that its exact nature had been debated for years, since it was first spotted by the Spitzer Space Telescope back in 2011. Because the white dwarf's own age and distance are well constrained, its faint companion offers an unusually clean natural laboratory for testing models of how cold planet-like objects cool and evolve over billions of years. Using James Webb's infrared spectrographs, astronomers, including researchers, publishing analyses. In 2025 and 2020, 6 have been able to tease apart the companion's temperature and composition with a level of detail that would have been impossible with any previous telescope, resolving discrepancies between how such objects are predicted to look and how they actually appear. It's a small technical story in itself, but it illustrates a larger point that matters for the dark matter heating search. Webb's combination of sensitivity and precision is good enough to characterize objects that are extraordinarily faint, extraordinarily cold, and sitting extraordinarily close on the sky to a much brighter neighbor. Exactly the observational challenge that any future search for a subtle excess of heat around an old white dwarf or neutron star will have to overcome. Objects this faint were not always found by professional astronomers working alone. In the years before Webb, projects like Backyard World's Planet 9 invited members of the public to comb through infrared survey images online, looking for the faint, slowly moving smudges that mark a nearby cold brown dwarf or Y dwarf, work that computer algorithms alone struggled to do reliably, because the human eye remains, even now, remarkably good at spotting a genuinely unusual pattern buried in noisy data. Volunteers using this platform have helped identify dozens of previously unknown cold worlds drifting near our solar system. Discoveries later confirmed and characterized in detail by professional follow-up observations, including, in some cases, by Webb itself. It's a reminder that the enormous datasets modern astronomy now produces, from Gaia's census of 2 billion stars to Webb's ever-growing archive of deep infrared images, are often too vast for any research team to comb through alone. And that some of the most interesting anomalies still get found because an ordinary person with no formal training noticed something that looked slightly out of place. This is also where the search connects to a much older and, in some ways, more successful tradition in physics, using astronomical objects as natural laboratories to test the properties of dark matter indirectly, because we cannot yet catch it directly in an underground detector on Earth. For decades, physicists have buried extraordinarily sensitive detectors deep underground, shielded from cosmic rays and other interference, hoping to catch the faint recoil of a dark matter particle striking an atomic nucleus. Those experiments have grown steadily more sensitive, ruling out large swaths of the possible properties dark matter particles could have, without yet finding a confirmed signal. The idea of using white dwarfs and neutron stars as cosmic-scale detectors offers a complementary approach. Instead of building an enormous, exquisitely shielded chamber and waiting for a single particle to strike it, you use an object that dark matter has already been striking, gravitationally trapped in, and slowly accumulating inside for billions of years, effectively turning an entire dead star into a detector with a surface area and an exposure time no laboratory on Earth could ever match. If this hypothesis is ever confirmed, the implications would ripple well beyond stellar astrophysics. Detecting dark matter heating in a white dwarf or a neutron star would not just be interesting. It would be one of the first pieces of direct physical evidence about how dark matter particles actually interact with ordinary matter at the particle level, a question that remains almost entirely unanswered, despite dark matter making up the majority of all matter in the universe. It could help pin down the mass and interaction strength of the particles involved, feeding directly back into the design of the next generation of underground detectors and particle colliders. And in dark matter-dense environments, like the crowded stellar swarm surrounding the supermassive black hole at the center of our own galaxy, it could, in principle, extend the observable lifetime of certain very old, very dense stellar remnants, adding a faint, persistent trickle of extra warmth long after their internal chemical heating mechanisms, like crystallization and neon sedimentation, have run their course. That crowded region at the center of our galaxy is worth describing properly, because it is precisely where any dark matter heating signal is expected to be strongest, and it is already one of the most intensively studied patches of sky in all of astronomy for an unrelated reason. Roughly 26,000 light-years from Earth sits Sagittarius, a star, a supermassive black hole with a mass about 4 million times that of our Sun, confirmed through decades of painstaking observations tracking individual stars whipping around it on tight, fast orbits. One particular star, catchily named S2, completes a full orbit around the black hole in only about 16 years, at times moving at several % of the speed of light, close enough and fast enough that its motion let astronomers test Einstein's general theory of relativity in one of the most extreme gravitational environments accessible to observation. The two teams who tracked these orbits for decades, led by Reinhard Genzel and by Andrea Ghez, shared half of the 2020 Nobel Prize in Physics for the achievement. That same gravitational extremity, the reason so many stars are crammed into such a small volume near the galactic center in the first place, is also expected to concentrate dark matter to unusually high densities, which is exactly why theorists modeling dark matter heating keep returning to this specific region as the most promising place to look, even though its extreme crowding and the intense, contaminating light from nearby stars and gas make it one of the hardest environments in the galaxy to study cleanly. An alternative, and in some ways even more promising, hunting ground lies much farther away, in a class of galaxies that barely deserve the name dwarf spheroidal galaxies. Objects like Draco, Sculptor, and Segway 1, small, faint satellite galaxies orbiting our own Milky Way, contain remarkably few stars, sometimes only a few thousand, and yet their stars move so quickly in ways only explainable by an enormous surrounding reservoir of dark matter that astronomers now consider them among the most dark matter-dominated objects known, with mass-to-light ratios implying that dark matter can outweigh their visible stars by a factor of 100 or more, because they contain so few stars and so little competing light or gas, and because their dark matter content is unusually concentrated relative to the small number of stars embedded within it. These dwarf galaxies offer a cleaner, quieter laboratory than the chaotic galactic center for searching out a subtle dark matter heating signal in any white dwarfs or neutron stars they happen to contain. Assuming future telescopes can resolve individual faint stellar remnants at such vast distances, a capability that instruments like the Extremely Large Telescope are specifically being designed to provide, it's worth stepping back even further to a question that physicists have been quietly turning over since long before the Gaia pileup or the launch of the James Webb Space Telescope. What happens to the universe and to its stars over spans of time so vast that billions of years starts to feel almost trivially short? In the 1970s, the physicist Freeman Dyson worked through the very far future of an expanding universe, layer by layer, projecting how stars would form more and more slowly as galaxies exhausted their gas, how the last true fusion-powered stars would flicker out over trillions of years, and how the white dwarfs, neutron stars, and black holes left behind would themselves eventually fade, evaporate, or decay over spans of time that make the current age of the universe, some 13.8 billion years, look like the very first fraction of a second of a much longer story. In Dyson's original accounting, white dwarfs were expected to cool, eventually, into cold, dark spheres of crystallized carbon and oxygen, sometimes poetically described as cosmic diamonds, radiating so faintly that after a few tens of trillions of years they would become effectively undetectable, indistinguishable from the blackness around them. If dark matter heating turns out to be real, even in the narrow extreme environments where it might plausibly operate, it wouldn't overturn Dyson's broader picture of a slowly darkening universe. But it would add a genuinely new variable to it, one that depends not just on a star's own mass and composition, but on how much invisible matter happens to be swirling around it. A white dwarf sitting in an ordinary low-density patch of the galaxy, far from the crowded environment near the galactic center, would still fade largely on schedule. But an identical white dwarf sitting deep within an unusually dark matter-rich dwarf galaxy might, in principle, hold on to a faint, additional glow for a while longer, powered by a slow, continuous trickle of captured and annihilating particles. It's a small correction to an enormous, slow-motion story, but it's exactly the kind of small correction that, if confirmed, would tell physicists something profound about the nature of the dark matter itself, since the size of the effect depends directly on properties, like the particle's mass and how strongly it interacts with ordinary matter, that no laboratory experiment has yet managed to pin down. That last point deserves care, because it's the one most prone to exaggeration. Even in the most optimistic, still unconfirmed versions of this hypothesis, dark matter heating would not make a star immortal in any meaningful sense. The heating effect scales directly with the local density of dark matter, and outside of a handful of extreme environments, like the innermost region of the galaxy, or the centers of dwarf spheroidal galaxies, believed to be unusually dark matter-rich, The ambient density of dark matter in most of the galaxy, including around our own solar system, appears to be far too low for this kind of heating to meaningfully slow a star's decline. Far from rewriting the ultimate fate of the universe, this hypothesis, if confirmed, would represent a narrow, fascinating exception that applies to a small subset of stars in a small subset of places. A footnote of extraordinary heating on top of, not a replacement for, the well-established slow fade that awaits the overwhelming majority of stellar remnants. That said, footnotes in physics have a way of becoming entire new chapters once they're properly understood. And the search itself is genuinely reshaping how astronomers think about where to point their instruments. Proposed future observing programs are now targeting the dense stellar populations near the galactic center specifically to search for excess infrared emission from old white dwarfs and neutron stars that cannot be explained by ordinary cooling physics alone. The reasoning is straightforward. If dark matter heating exists at any meaningfully detectable level, this is the environment where the effect should be largest and therefore easiest to catch. Assuming astronomers can first account for every other source of contaminating heat and light in one of the most crowded and complicated regions of the sky, there is also a broader instrumental story unfolding here, one worth appreciating on its own terms. The James Webb Space Telescope, launched in December of 2021, and now several years into its scientific mission, was designed from the outset with an extraordinary sensitivity to infrared light, the part of the electromagnetic spectrum where cool, faint objects, including old white dwarfs, neutron stars, and the very earliest galaxies in the universe, reveal themselves most clearly. Its 6.5-meter primary mirror, built from 18 hexagonal gold-coated segments, gathers roughly 6 times the light-collecting area of the Hubble Space Telescope. And its instruments, including the near-infrared camera, the near-infrared spectrograph, and the mid-infrared instrument, allow astronomers not just to detect faint sources, but to measure their precise temperatures and chemical compositions in detail. This combination of raw sensitivity and spectroscopic precision is exactly what makes Webb such a promising tool for both halves of this story, confirming, with ever greater confidence, the ordinary physics of white dwarf crystallization and sedimentation, while simultaneously pushing the search for a genuinely exotic dark matter heating signal into territory no previous telescope could reach, getting ice. An instrument this sensitive into position was itself one of the most technically demanding feats in the history of spaceflight. To detect the faint infrared glow of an ancient white dwarf, or the even fainter glow that a hypothetical dark matter heating signal might add on top of it, Webb's own instruments have to be kept extraordinarily cold, since any warmth in the telescope itself would otherwise drown out the faint infrared light it is trying to measure. In the same way, a bright flashlight held next to your eyes would make it impossible to see a distant, dim star. Engineers solved this by placing Webb nearly 1 million miles from Earth, at a gravitationally stable location called the second Lagrange point, far beyond the orbit of the Moon, and by unfolding a tennis court-sized 5-layer sunshield behind it, each layer thinner than a human hair that blocks heat from the Sun, the Earth, and the Moon, all at once, allowing the telescope's mirrors and instruments to passively cool to roughly minus 370 degrees Fahrenheit. Webb launched on Christmas Day of 2021. Folded up like origami to fit inside the nose cone of an Ariane 5 rocket, and spent the following month unfolding itself in space, a sequence involving hundreds of individual mechanisms, any one of which failing could have doomed the mission, before finally reaching its observing position roughly 1 month after launch and beginning several more months of careful calibration. That such a fragile, complex instrument unfolded successfully on the first attempt, with no possibility of a repair mission at its remote location, is part of why astronomers now speak of Webb's data with such confidence when tackling questions as subtle as a fractional degree temperature excess on a dying star. Webb will not be working alone for long. The Nancy Grace Roman Space Telescope, expected to begin science operations later this decade, will pair a mirror the same size as Hubble's with a field of view roughly 100 times larger, allowing it to complement Webb's narrow, exquisitely detailed view with enormous, wide-field infrared surveys covering huge swaths of sky in a single pass. Exactly the kind of broad, systematic search needed to catch rare, anomalous objects that a narrower instrument like Webb, however sensitive, would simply never happen to point at. Ground-based giants currently under construction will add still more raw light-gathering power once they come online. The extremely large telescope, being built in the Atacama Desert of Chile, will carry a primary mirror roughly 39 meters across, assembled from nearly 800 individual hexagonal segments, making it, once complete, the largest optical and infrared telescope ever built, while the 30-meter telescope, planned for a high-altitude site, aims to bring comparable resolving power to bear from the other hemisphere. Together, these next-generation instruments promise to extend the reach of this search to fainter, more distant, and more crowded stellar populations than are currently accessible even to Webb, providing the observing time and sky coverage that any statistically convincing detection of dark matter heating would ultimately require. A completely different kind of observatory, sensitive not to light at all, but to ripples in the fabric of space-time itself, is also being built with white dwarfs partly in mind. The Laser Interferometer Space Antenna, a joint European Space Agency and NASA mission expected to launch in the 2030s, will consist of 3 spacecraft flying in formation millions of miles apart, using laser beams to measure changes in distance between them smaller than the width of an atom. Changes caused by passing gravitational waves, the same kind of ripple first directly detected from colliding black holes by the ground-based LIGO Observatory in 2015. Unlike LIGO, which is tuned to catch the brief, violent chirp of black holes merging, this space-based observatory will be sensitive to a lower, steadier frequency range, one dominated in our own galaxy by tens of thousands of white dwarf binary pairs, slowly spiraling toward each other over millions of years. This matters for our story because those same tight, merging white dwarf binaries are the ones that eventually detonate as type Ia supernovae once their combined mass creeps past the Chandrasekhar limit, and a space-based gravitational wave observatory would, for the first time, let astronomers watch that slow spiral inward directly, tracking individual binary systems for years at a time and building an entirely independent census of how common these eventual detonations and the extreme stellar remnants they sometimes leave behind actually are throughout the galaxy. It's also worth being honest about the skepticism that surrounds even the best version of this hypothesis, because good science depends on taking that skepticism seriously rather than waving it away. Many astrophysicists studying white dwarf cooling point out that crystallization and neon sedimentation already explain the overwhelming majority of the anomalous heating observed so far, and that invoking dark matter as an additional heat source, on top of mechanisms that are already doing most of the explanatory work, risks reaching for an exotic answer before the mundane one has been fully exhausted. This is a healthy and necessary tension in the field. Extraordinary claims, the saying goes, require extraordinary evidence, and a claim as significant as the first indirect detection of dark matter interacting with ordinary matter would need to survive an enormous amount of scrutiny, ruling out every conventional explanation before the physics community would treat it as established. Even the researchers who first proposed dark matter heating of neutron stars and white dwarfs frame their own work carefully as a testable prediction and a search strategy, not as a discovery. And they have been explicit that current instruments, Webb included, are only now approaching, not yet exceeding, the sensitivity needed to detect the smallest predicted signals in the most promising environments. Similarly, the dark star candidates identified in early James Webb observations remain genuinely contested. Several independent research groups have proposed alternative explanations for the same unusually bright, unusually red, extremely distant objects that Catherine Fries and her colleagues interpreted as candidate dark stars, including the possibility that they are simply compact, rapidly star-forming galaxies seen at an early and unusual stage of their development, or that their light is dominated by a rapidly growing supermassive black hole at their center rather than by any large-scale stellar population at all, dark matter-powered or otherwise. Untangling these competing explanations requires more detailed spectroscopy than has yet been possible for the faintest and most distant of these candidates, spectroscopy that upcoming, longer Webb observing programs are specifically designed to obtain. None of this guarantees an answer anytime soon. Dark matter has, so far, proven remarkably good at evading every method physicists have devised to pin it down directly, whether through underground detectors, particle collider experiments, or astronomical searches like this one. It remains entirely possible that the particles making up dark matter interact so weakly with ordinary matter that even a white dwarf sitting at the dense heart of the galaxy for 10 billion years would show no detectable heating at all, and that the entire search comes up empty, ruling out certain classes of dark matter candidates without ever finding a positive signal. That would still be valuable science. In physics, learning what something is not, precisely and rigorously, is often just as important as learning what it is, steadily narrowing the space of possible explanations until only the true one remains. The field has been burned by false alarms before, and it's worth remembering one of them here, because it shows exactly the kind of caution this entire documentary has tried to model. In 2014, 2 independent research teams, studying X-ray light from galaxy clusters and from the Andromeda galaxy, reported an unexplained, faint emission line at an energy of about 3.5 kilo electron volts, a signal that did not match any known atomic transition from ordinary matter, and that tantalizingly matched predictions for the decay of a hypothetical dark matter candidate called a sterile neutrino. For several years, the 3.5 kilo electron volt line generated enormous excitement. Dozens of follow-up papers and serious proposals for dedicated future missions built specifically to study it further. Then, gradually, the signal began to weaken under closer scrutiny. Some follow-up observations failed to reproduce it at the expected strength. Careful reanalysis suggested that at least part of the signal could be explained by an ordinary, mundane atomic transition in charged potassium ions, a contaminating astrophysical process with nothing to do with dark matter at all. The line has not been definitively debunked, and a minority of researchers still consider it an open, unresolved anomaly worth further study. But it serves as a sobering case study, an exciting, statistically significant signal, initially interpreted as possible evidence of dark matter, that mundane astrophysical explanations have steadily eaten away at over a decade of follow-up work. Any future claim of dark matter heating in a white dwarf or neutron star will face exactly this same gauntlet of scrutiny before the physics community accepts it. And given how the 3.5 kilo electron volt story unfolded, that scrutiny is entirely appropriate. But it's also entirely possible that somewhere in the crowded stellar swarm near the galactic center, or in the dense heart of a nearby dwarf spheroidal galaxy, an old white dwarf or neutron star is quietly glowing just a little warmer than the standard cooling models, crystallization and sedimentation included, can fully explain. If that excess is ever confirmed, cross-checked against every known conventional heating mechanism, and reproduced independently by multiple research teams, it would represent the first direct astrophysical evidence of dark matter interacting with ordinary matter anywhere in the universe, a result that would reshape particle physics, cosmology, and stellar astrophysics all at once. What makes this story so compelling is not that scientists have already found something impossible. It's that they found something genuinely strange, a population of stars refusing to cool on schedule. And rather than reaching for the most dramatic explanation available, they patiently worked through the physics, piece by piece confirming crystallization, confirming neon sedimentation, and only then turning to the far more speculative, still unconfirmed question of whether an invisible substance that makes up the majority of all matter in the universe might also be leaving its faint, warm fingerprint on the slowly fading embers of dead stars. There is a broader lesson buried in this story about how science actually makes progress, one that applies far beyond white dwarfs and dark matter. It would have been easy, back in 2019, for someone encountering the Gaia pileup for the first time to reach immediately for the most exciting possible explanation, to announce that dead stars had discovered some exotic new source of eternal fuel. Instead, the physicists who took on the puzzle did the slower, less flashy work first, checking whether an already known, non-exotic process, crystallization, could explain what they were seeing and only turning to sedimentation, and later to the far more speculative idea of dark matter heating, once the simpler explanations had been tested against the data and found insufficient on their own. This is, in miniature, how most real scientific progress happens. The exotic explanation is rarely the first one reached for, and it is rarely the right one, but every so often, after the mundane explanations have been carefully exhausted, a genuine anomaly remains, and that remainder is where entirely new physics tends to hide. Whether the current remainder in white dwarf and neutron star cooling curves, if any remains at all once every conventional mechanism is fully accounted for, turns out to be evidence of dark matter, or simply evidence of some further conventional process not yet identified, is a question this generation of astronomers, working with an unprecedented combination of Gaia's statistical reach and Webb's exquisite sensitivity, is now in a genuinely strong position to answer. The white dwarfs that started this story are not defying physics. They are following it more intricately than anyone expected, revealing that their interiors are layered, dynamic, chemically active environments, still capable of generating heat billions of years after their nuclear fires went out, through the ordinary, well-understood processes of freezing and sinking that operate at pressures and densities almost impossible to reproduce anywhere on Earth. Whether an additional, far more exotic contributor, the trapped and annihilating or endlessly scattering particles of dark matter, is also at work in the most extreme of these environments remains one of the open questions at the frontier of astrophysics, actively being tested right now with some of the most sophisticated telescopes humanity has ever built. It's worth sitting, for a moment, with just how many separate, hard-won pieces of physics had to come together to make this entire story possible to tell at all. It took the quantum mechanics of the 1920s to explain why a white dwarf doesn't collapse. It took Chandrasekhar's ridiculed, later vindicated calculation to explain why some stars collapse further still into neutron stars, and why others detonate as supernovae bright enough to measure the accelerating expansion of the universe. It took Zwicky's irritable insight and Rubin's painstaking measurements to establish that most of the universe's mass is invisible in the first place. It took Bell Burnell's sharp eye on a strange regular radio pulse to confirm that neutron stars are real. It took decades of theoretical work on how dark matter particles might scatter and settle inside dense objects to predict a signal anyone could even think to look for. And it took two of the most ambitious space telescopes ever built, Gaia patiently mapping 2 billion stars, and Webb peering deeper into both the coldest nearby objects and the earliest, most distant ones, to finally gather data precise enough to test all of it at once. No single discovery in this documentary explains the whole picture on its own. It is the layering of all of them, built up over the better part of a century, that has turned a strange pile-up of white dwarfs into a genuine, testable window onto the deepest unanswered question in modern physics. What remains genuinely unknown is not small. Physicists still cannot say with any certainty what dark matter particles actually are. Whether they are WIMPs, axions, sterile neutrinos, some combination of several candidates, or something no one has yet proposed. They cannot yet say with confidence whether the subtle cooling anomalies still being refined in white dwarf and neutron star data, once every known conventional process is fully subtracted away, will turn out to hide a genuine dark matter signal or simply more ordinary astrophysics waiting to be understood. They cannot say whether the handful of candidate dark stars glimpsed in Webb's deepest images are truly a new class of object from the universe's first few 100 million years, or simply ordinary early galaxies wearing an unusual disguise. Each of these open threads is being pulled on right now by researchers running new calculations, proposing new observations, and building new instruments specifically designed to settle questions that have remained open for decades. The oldest stars in the galaxy are not immortal, but they are turning out to be far more interesting in their old age than anyone expected, still quietly generating heat, still holding secrets about the deepest physics of matter itself, long after the rest of the universe assumed they had nothing left to say. Somewhere out there in the crowded, ancient light near the center of our galaxy, a faint infrared glow may be waiting, patient as the stars themselves, for an instrument sensitive enough, and a team of scientists careful enough to finally read what it has to tell us. For now, the honest answer is simply that we don't know, and that not knowing is precisely what makes this such a good time to be paying attention. The datasets capable of settling this question: Gaia's census of 2 billion stars, Webb's ever-deepening infrared archive, the underground detectors steadily narrowing the possibilities. The future gravitational wave observatories designed to watch white dwarf binaries spiral together in real time are either already in hand or actively under construction, arriving faster than most working astrophysicists expected even a decade ago. Somewhere in the gap between what has already been confirmed, the quiet, elegant physics of a freezing, sedimenting stellar core, and what remains only a carefully reasoned possibility, an invisible substance leaving its faint thermal signature on the embers of dead stars, sits one of the more genuinely open frontiers left in modern science. And it is being worked on, patiently, star by star, right now.